Hi, my name is Rebecca Willet, and it's my pleasure to deliver this EUSIPCO plenary lecture on inverse problems in imaging, methods, sample complexity, and robustness. And the work I'll be talking about today is joint work with my student, Davis Gilton at UW-Madison, and former postdoc and now assistant professor at the University of Marquette, Greg Ongi. The basic problem that we'll be talking about today concerns inverse problems of imaging of the general form y equals ax plus epsilon. So in this context, x would be the image of interest, the thing that we'd like to be able to reconstruct. And we're concerned with the scenario where we don't get to observe x directly, but rather only get to observe it through some sort of distortion or optical system that is denoted by this matrix A. So this could correspond, for instance, to missing pixels, or a blur, or downsampling, or even MRI measurements. And so what we'd like to be able to do is to take these distorted measurements y, which might be contaminated by some noise epsilon, and recover x from y. So this is an old problem that's been considered for many, many years. And if we think about the simple example of deblurring, for instance, we can see where some of the core challenges lie. So given the formulation on the previous page, you might think, well, I could just solve this using least squares, and I've got some equations highlighting that here. And we can see that if we just use the least squares equation, then our estimate x hat is x plus some operator that depends on our forward model times the noise. So if we look at this in action, we can see our blurry image, and if it has no noise whatsoever, then this least squares solution works perfectly, because if epsilon is 0, then we just get x hat being equal to the true image x. But even with a tiny amount of noise, so small that you might not even be able to see it, this can create a wildly different solution. And the challenge is that some of the eigenvalues of x transpose x here can be very small, so that when we take the inverse, we get huge multiplicative factors that are multiplied by even a small amount of noise to create big blow up in some of the pixels. So a classical approach to address this problem is to regularize the solution, to add on a term, in this case the sum of the squares of the pixels in x, in order to prefer solutions that don't have these pixels that have values blowing up. And in this case, there's even a nice closed form solution. And when we try it out, what we see is a result that looks significantly better when we've got noisy data than we could get with classical least squares. Okay, so this approach, Tikhonov regularization or ridge regression, dates back many decades, almost a century now. And people have built upon it in some pretty significant ways over the years. People have considered other kinds of regularizers, including total variation, where we look at the first order differences between pairs of neighboring pixels, either horizontally or vertically, or both. We look at wavelet sparsity, or even looking at the geometry and structure of different patches within images. All of these different tools can be used to create regularizers that help steer an estimator of an image in this inverse problem setting towards something with the kinds of structure that we hope and expect. So more generally, we can think about estimation in inverse problems as computing an estimate x hat by searching over all candidate images x and choosing one which minimizes not only the error with respect to our data and our forward model A, but also which gives us a small value of some regularization parameter. But all of the methods I've talked about so far choose this regularizer a priori based on something like smoothness or a geometric model of the content of images. But more recently, researchers have been considering trying to actually learn good regularizers using training data. And there's actually been quite a bit of literature in this area. I'm just referencing two recent tutorial or review articles that give a broad overview of the literature. But today what we're going to do is we're going to look at certain classes of approaches that are guided towards learning how to reconstruct images in this inverse problem setting. And along the way, we're going to be considering some key trade-offs that are involved. The first of these is generality versus sample complexity. So we're going to look at methods that do or do not leverage knowledge of this forward model A and how that affects sample complexity. We'll also be looking at trade-offs related to reconstruction speed and convergence guarantees. And finally, and with some particular attention, we're going to look at sensitivity to model mismatch. What happens when we try to train a method to solve a particular inverse problem, but then when we deploy it out in the real world, we have a slightly different forward model. Okay, so let's just start by talking about some of the core classes of methods. So within these different categories that we'll talk about, we're going to see multiple different examples, or there exist many different examples, and we'll just highlight a couple to give you a flavor of the different methods that are out there. So the first category is what I call model agnostic. And the key idea here with model agnostic methods is that for the reconstruction process, very limited, if any, information about the forward model A is being used. I think this is clearest in the context of a superresolution example. So the idea here is that Y, our observations, consist of a low resolution image. And so if I wanted to use a convolutional neural network, for instance, or train a neural network in order to perform superresolution, I might have a pipeline that, for instance, first does a very kind of rough first order approximation to an inverse of A. So in this context, for instance, we might just use bicubic interpolation to get an initial coarse high resolution image, and then use a trained neural network to remove different blocky or blurry artifacts in that bicubic interpolation, so that in the end we get high quality, high resolution reconstructions. There's a number of different papers within this category, and what we can see is that detailed information about A is not used anywhere. We only use this sort of coarse initial estimate right at the beginning. This method is particularly effective in the context of problems like superresolution or deblurring, where we can get a pretty good initial estimate with minimal knowledge about A. But in other settings that we'll see, such as compressed sensing or MRI reconstruction, this approach has some more significant limitations when we try it out in practice. And so this brings us to the second category of methods that we want to explore, in particular, decoupled methods. And by decoupled, what I mean is that we decouple or separate out the process of leveraging our training data or performing learning and anything that has to do with our forward model A. There's a number of different approaches within this category, and I'm just going to pick on one to be concrete, but they share many key salient features that I'll highlight. So in particular, I want to explore an approach that involves using generative adversarial networks, or more generally generative models that we can learn in order to solve inverse problems. So as I said before, we're interested in learning a regularization function R that's going to allow us to get good reconstructions. So let's imagine that all of our images that we care about lie on some sort of low-dimensional submanifold. So they might have many, many pixels, but there's only a subset of images that are, say, 256 by 256 that really exhibit the kinds of structures that we're interested in. If we knew what that manifold was, then we could use it to design a regularizer. And perhaps most naively, we could just say that the value of our regularization function is 0 if the image lies on the manifold and infinity otherwise. So now you might ask, well, is there a way then to somehow learn what that manifold is so that we can have a regularizer akin to this idea? And this is where learned generative models come into play. Okay, so we started here by saying that we wanted to have a regularizer that reflected information about the manifold. So what we might do is we might try to use our training data to learn a generator. So this is often used, represented using a neural network, but we can still think about it as a function. a function that outputs an image that is on this image manifold given some lower dimensional input. So if we had this generator, then we can use it to represent the manifold. Or in particular, we can have our regularization function R be 0 whenever we have an image that's in the range of this generator or that could somehow be output by the generator, and otherwise be infinity. So you might have seen examples of these kinds of generators or their outputs on the internet or in different pieces of the literature. But the basic idea is that we would have some sort of low dimensional input, and perhaps even with a random input, the output of the generator would correspond to a face or a picture of an animal or some other kind of image that looks very realistic and natural to us, even though it might not have existed in any training data set. So in this first stage of training the generator, we're leveraging our training data, but there is nothing here so far that is using our forward model A. Training the generator is totally independent of the forward model A. So in the second stage of this process then, what we do is we use our observation Y and our forward model A in order to find an image that fits the data and is in the range of this generator. So we search over all images in the range of the generator and choose the one that gives us the best fit to the data. So at this point, we're done training, but we use our forward model, and this is why we call it decoupled. We've got the training phase up here, and we've got the reconstruction phase down here. Now, one of the nice features of this approach is that you can run this optimization problem all the way to convergence, and you can actually evaluate whether or not you've converged, whether or not you've actually somehow found a local minimizer of this optimization problem. But you don't know ahead of time how many different iterations you're going to need or what kind of computational budget you're going to need in order to perform the reconstruction. Another feature of this approach is that it works very well when you've got large numbers of samples, so that if I were to train a generative model based on a convolutional neural network, I can get good reconstructions using this decoupled approach. But for this approach and for other decoupled approaches where we separate out the learning process from the reconstruction process, if we start cranking down the number of training samples that we use for training, suddenly the reconstruction quality degrades in a significant way. Now, you might be saying, well, is this really a big problem? Because obviously there are lots and lots of images and lots of data sets. It really depends on the context. So if I wanted to reconstruct images of cats, then maybe this isn't a problem because there really is an infinite number of pictures of cats on the internet. But there are many settings, including medical imaging, where the amount of training data is pretty limited relative to the quality and size of the reconstructions that we want to be able to achieve. And so thinking about how much data is required in order to achieve good reconstructions is a pretty important challenge in these and other applications. So let's just take a small break to think about why these decoupled approaches. And again, I'm not picking on the generative models in particular. I think of it as being just one example within this decoupled framework where we separate out the training from the leveraging of the forward model. Let's think about why they might have challenges in terms of sample complexity, why they start to break down when we have a small number of training samples. For me, the easiest way to think about this is in the context of probability density estimation. So imagine that we were trying to solve an inpainting problem. So we only observe a subset of the pixels in the image, and we want to be able to fill in the remaining pixels. When we use these decoupled approaches, the training phase is more or less learning key facets of the probability distribution over the space of all images. And then once we have our observation and our forward model, we can try to find the image that has a high likelihood, more or less, according to this probability distribution that fits the data. But nevertheless, I have to learn this entire distribution. In the context of this inpainting example, though, it's pretty clear that learning the full distribution over all images requires learning a lot of stuff that I don't need. In particular, if I'm just trying to fill in these missing pixels in the image, there's a lot of stuff going on the periphery of the image that I would have to learn when I learn this probability distribution, but which is totally irrelevant to my task at hand, to the problem of trying to fill in these missing pixels that are in the middle of the image. So in contrast, you might say, well, what I really care about is trying to understand a conditional density. I want to understand the distribution of the middle portion of the image, or I want to understand the distribution of the missing pixels conditioned on the observed pixels. And I'm talking about this in the context of inpainting because it's very clear to think about what these null spaces and ranges are, but this is a general principle that holds up across linear inverse problems. And we have a wealth of literature in the statistics community that studied trying to estimate conditional densities. And that literature shows us that those densities can be lower dimensional and smoother than the full or joint densities, which can thus reduce the sample complexity or the amount of data that we need. And so the claim I'd like to make is that by leveraging information about the forward model A from the beginning gets us closer to this more idealized scenario of trying to estimate the conditional density, and thus reducing the amount of samples that we're going to need in order to learn how to do good reconstructions. So another way of saying this is that estimating the conditional density can require far fewer samples than estimating the full density. So if we know what this forward model is a priori, we should be utilizing it within the learning process. And so that brings us to this third category of approaches that I wanted to describe, unrolled optimization. So let's start off just by talking about gradient descent. So imagine that we already had a good regularization function and it was differentiable. Then how would we actually compute an estimate? Well, what we would do is we would start with this optimization problem, and then we would start with some initial estimate, say some weight factor times A transpose Y. And then at every iteration, we would update our estimate by taking our past estimate and taking a step in the direction of the negative gradient of our squared error and the negative gradient of our regularizer. So if we were to do this for a finite number, let's say B iterations, then we can write this process with a simple block diagram. So we take our input and we feed it into a block, where the top branch of the block is essentially taking this step in the negative gradient with respect to our squared error, and the second block is accounting for our regularizer. And then we repeat this for each one of the iterations, and we finally get an estimate. Okay, so all of this assumes that we know what our regularizer, or at least what its gradient is. And so the idea behind an unrolled gradient descent network is that we basically take this step within the gradient descent framework and replace it with a learned neural network. And so what we have is an overall end-to-end framework where within each block we've got two branches. One that accounts for our forward model A and our squared error with respect to our data, and the second which accounts for our regularizer R. And so now what I can do is I can train this network, or I can choose the weights on these different learned components in order to minimize my training loss. But because my initial estimate is being fed through this network that automatically from the beginning accounts for my forward model A, my learned estimate is going to depend on A as well as the training data. I've integrated A into the training process. I'd also like to consider a variant of this called Neumann Networks, which was developed with my student Davis and postdoc Greg. So again, we start off by saying, imagine that we had a differentiable regularizer R, and we wanted to solve this optimization problem. Well, what I can do is I can think about the solution to this optimization problem as corresponding to the inverse of an operator corresponding to A transpose A times the gradient of R, all multiplied times A transpose Y. If this operator were linear, this operator in parentheses were linear, then I can think about its inverse using a Neumann series expansion, which is akin to a power series expansion. And if I were to truncate that series to just have B terms, then what I would see is I would have this expression here that again accounts for my forward model A and the gradient of my regularizer R, and that gets multiplied times my initial estimate A transpose Y. And so I can think about this as being akin to sort of a fixed point operation, and I can again write it using a block diagram as I have here on the bottom. And similarly to what we did with unrolled optimization, we can then say, let's imagine that we take the gradient of our regularizer here and just replace it with a learned neural network. So this looks very similar in spirit to the unrolled optimization approach of the previous slide. But one thing I want to emphasize is that our final estimate here is not the output of the final block, but rather the sum of all of the outputs of all of the different blocks. And this turns out to make a pretty significant difference when it comes to actually making these things work in practice. Because a change to this network here is felt pretty immediately by the final estimate, training becomes much easier, much more stable with respect to hyperparameters and step size, and we're able to find good estimators relatively easily. Another thing that I want to mention about these Neumann networks is that they have a nice tie-in to some of the things that we talked about earlier about conditional density estimation. So in particular, you could imagine saying, how could we characterize the best possible estimator that we might be able to compute? The estimator where if we were to plug in y and look at its mean squared error relative to the true image x and just average this over the distribution of x's and y's, which estimator would give us this minimum mean squared error? So we're going to call this rho star. And in the context of our particular setup with forward model A, we can actually write down an explicit expression for what that optimal reconstruction reconstructor would look like. And with just a few algebraic manipulations, we can see that there are two key terms. One that corresponds to a pseudo-inverse of A times Y, which I've expanded using a Neumann series, plus another term that depends on the conditional density. So in the context of inpainting, again, this would correspond to the expected value of the missing pixels conditioned on the values of the observed pixels. Now what we can also do is we can think about this Neumann network and what it's actually computing with this sort of block diagram with B different blocks. And again, using some algebraic manipulations, we can show that the output of this Neumann network that we're going to train corresponds to a truncated Neumann series of the pseudo-inverse that corresponds to a close approximation to the green block in the optimal reconstructor, plus another term that depends on the learned component, the learned neural network. So we can see in this green term, nothing here at all is learned. We've got all of the learned components in the red block, and this corresponds to the conditional expectation that showed up in the optimal estimator. And so the hope is that by using this Neumann network architecture, what we are going to be learning is going to, and trying to minimize the mean squared error, is going to adapt to this conditional density. Okay, so I just want to mention one other thing very briefly because we're going to see some empirical results in a second. On the top here, I've got the Neumann network that I just described to you. On the bottom, we're going to also consider a preconditioned version of it. The basic idea here is that we input at the very beginning of the overall network a better initial estimate that we compute just using Tikhonov regularization. And using the mathematics of Neumann series expansions and some other tools, we're able to figure out how we should actually adapt the different blocks within the Neumann network in order to account for the new initialization. And this gives us an additional performance boost. So far, we've seen these 4 different categories of methods, and now what we're going to do is just see a representative from each category in action empirically. So in particular, for these agnostic methods, we're going to consider a residual autoencoder. It's not quite as agnostic in this case as I had led you to believe, in that the input does depend a little bit on the true forward model A, just to make it the most generous comparison that we could. We'll also consider these decoupled approaches where we do all of our training kind of in a way that is agnostic to the forward model, and we only use the forward model in the final stage. We'll look at unrolled gradient descent and the Neumann network. So first I'll just show you a little anecdotal example. So in the top row here I've got the original, the result of the Neumann network, unrolled optimization, the method that does not use the forward model A, and this decoupled approach. And right below that, you can see what was input to the network, the blurry image that was input to the network, and then a series of residuals for these different estimators. And you can see where these residuals have been multiplied by, I think it was 5, in order to just highlight the details in the residuals. And so you can see with only 2,000 training samples, we're able to get significantly better reconstructions using these Neumann network ideas than with other approaches. And even when we increase the number of training samples, we can see there are still some advantages in terms of the visual quality. Now, we did experiments like this across the board and folded in this preconditioning idea that I just mentioned to you. And in particular, we considered deblurring, superresolution, compressed sensing, and inpainting. And we looked at examples from STL, CFAR, and Celeb-A datasets. And so across the board, what we see is that these methods that, first of all, integrate A into the training process from the beginning, and which exploit this special architecture of the Neumann network, give us high peak SNRs for a range of different sample sizes, training sample sizes. We also can see these ideas in action in the context of MRI reconstruction. So in green, I'm showing you 3 different learned estimates: the preconditioned Neumann network, the Neumann network, and modal, which is widely considered to be the state-of-the-art for MRI. And you can see that all 3 of these learned methods are getting high PSNRs from 33 to 35. And computing these reconstructions, because we only have a finite number of blocks B, which is on the order of 10, we're getting small numbers of seconds required to compute the estimate. Again, on the top I've got the actual estimates, and on the bottom I've got the residuals, and then here I'm showing the Fourier or K-space mask used to collect the actual MRI data. We can contrast this with what we get if we do total variation regularized reconstruction, something I mentioned back at the beginning, where we get a lower PSNR and we require significantly more time in order to compute the reconstruction. And so this highlights some of the potential of these learned methods. I mentioned at the beginning some of the key trade-offs that we wanted to explore in the context of learning to solve inverse problems. So the first was generality versus sample complexity. So let's think about the contrast between methods like the Neumann network, which use the forward model A throughout the training process, and decoupled approaches like those based on generative models. So what we've shown with these experiments and some of these arguments based on conditional densities is that leveraging the forward model A during training does give us lower sample complexity. But it's worth noting that then every time I've got a new forward model, I have to retrain my model. I don't have a general purpose tool that I can use for any inverse problem under the sun. So in contrast, these decoupled approaches have the key advantage that once you've done your training, you can take that trained model and just hold it fixed and hopefully use it for a wide variety of inverse problems. Another key trade-off that I've hinted at is between reconstruction speed and convergence guarantees. So trained models that plug into iterative methods can be slower. So for instance, if I were to train a generative model and then try to find the optimal input to that generative model, one of the benefits is that I can actually run that all the way to convergence. But one of the disadvantages is that that can require a large number of iterations and take a lot more time to compute an estimate. In contrast, methods like the Neumann Network or Unrolled optimization fix that computation budget a priori. So you get a very fast method, but it can be kind of difficult to characterize or say anything about convergence. Finally, there's a trade-off that I want to give a little bit more detail to on reconstruction accuracy versus sensitivity to model mismatch. So in particular, you could imagine taking a learned neural network and then trying to use it in a context in which that it wasn't necessarily designed for. And the question is, what kind of effect does that have, and can we mitigate any challenges associated with it? So in this portion of the lecture, I want to be a little bit less constrained about thinking about a particular algorithm that I'm using to do the reconstruction. I just want to think about having some sort of block that I've learned that inputs data y and outputs an estimate x hat. This reconstruction function might depend on my forward model A, and it's also got some learned parameters like learned weights in my neural network that I denote by phi. So I can always think about my estimate x hat as being a function of my data and my neural network parameters and potentially my forward model A. And of course, an example of this is exactly the Unrolled gradient descent network that we were just talking about, where it depends on A, it depends on my forward model, and it depends on my neural network, and it depends on my data Y. Okay, so this is sort of the general context in which we're going to think about robustness to model drift or model mismatch. So in particular, the idea is that we're going to think about what happens when we use forward model A0 when we're training, but then at deployment time have data corresponding to a different forward model A1. So let's think about this in the context of MRI, because I think this is one context in which this problem is very common and would arise quite a bit. So when you run an MRI scan, there's a lot of different kind of design parameters that you can choose. You can decide whether you want Cartesian sampling or radial sampling or spiral sampling. You can decide how much undersampling you want to do, which relates to the acquisition speed. How many you might want to use it on different scanners that have different numbers of coils or different coil sensitivity maps. So trying to design a method that's going to work in all of these different contexts can be quite challenging. And there has been work, including from Anders Hansen's group just last year, that shows if we were to train a network for one of these acquisition models and then try to leverage that learned network in a slightly different setting, that things can actually go quite badly. They even showed an example where they went from 4-fold undersampling to 3-fold undersampling. So they actually had more data and they were in a more advantageous scenario at deployment time, and they still got a degradation in performance because they hadn't trained for that new acquisition setting. Now you might say, well, how about every time I tweak my MRI system, I just train an entirely new network from scratch? And I would argue that that's not really a feasible solution, in part because that can be pretty time consuming, but also because we don't generally have large publicly available data sets that we don't have to worry about the privacy of. So we don't want to assume that we're going to have everybody with an MRI scanner having constant, continuous access to the same ground truth data set of images to retrain on. Now, you might also argue whether this is really necessary. So for instance, in the context of the gradient descent network, we had this forward model A just built right in. And that corresponds to feeding in my forward model into this general, more generic block of reconstruction block that I wrote here. So you might say, well, why can't I just then replace A0 with A1? Or in the context of this gradient descent network, just take all these A's and instead of using A0 here, use A1 here. Wouldn't that just accomplish what I need without me having to do any retraining whatsoever? And the answer is no. And so let me just show you a couple of examples to kind of highlight that. So here's my original image, and then this was subject to a motion blur that I then tried to correct for using a learned model. So in this context, we've got sort of the ideal scenario where I trained for exactly the motion blur that I actually have at deployment time. And in contrast, on the bottom, I'm looking at what happens when my motion blur at deployment time is different than the motion blur at training time. So here, when I use no model adaptation, I get some pretty significant degradation in quality. This is much worse than what I would get if I knew the motion blur when I was training. But in contrast, if I do model adaptation, which is an approach I'm going to describe in just a couple of seconds, then I can get much higher PSNRs and much higher visual quality. And I'm even just going to zoom into these images to kind of highlight some of the visual differences on the screen here. And this is true in general. So I'm going to present some generic approaches that aren't designed for a specific class of forward models. Again, here's my original image. Here's sort of the best quality I can get if I know exactly the MRI acquisition protocol when I'm doing training. If I change my acquisition protocol at deployment time and don't account for it at all, suddenly I get a lot of blurring, features get erased, but I also get some giant artifacts introduced. But if I were to start using model adaptation, the methods that I'm going to talk about in just a second, then we get significant improvements in quality that gives us an image that's ultimately on par with what we could have had if we had known the right MRI acquisition protocol from the beginning. Okay, so here's the general task that I want to present. We're going to start off by training a reconstruction network for a known forward model for a particular MRI acquisition protocol. And then at deployment time, we want to be able to take that trained reconstruction network and adapt it to a new forward model or a new MRI acquisition protocol. And we want to do this in a way that doesn't depend on us having access to a huge database of ground truth images. And we want to be able to do it potentially without knowing all the exact parameters of the new forward model. So here's the basic setup. So when we're training, just like we talked about in the first half of today's lecture, we're going to assume that we have XY pairs that all correspond to some original forward model, A0. Then after deployment, we're going to have a collection of calibration samples. And for the calibration data, we only have the Ys. This is like only having access to the MRI scans without knowing the ground truth MRI images that led to those scans. But they all correspond to the same new forward model A1. And again, it's a similar kind of setup, we just have a different forward model here. Now at this point, I'd like to highlight the difference between what we're talking about here with model drift and model adaptation and terms you might have already heard of related to distribution drift and domain adaptation. So with distribution drift, we've got some underlying probability distribution of our images and data. And with distribution drift, that distribution changes in some unknown way between when we train our system and when it's deployed. And the problem of domain adaptation is to train one of these networks with many samples from the original distribution, and then to adapt that trained network to a new distribution using just a small number of samples from that new or second distribution. Now in contrast, when we talk about model drift in our context, here this distribution is actually changing in a known or partially known way. So in particular, we know that there's a linear relationship between y and x, And we know it's that relationship that's changing. And we might even know exactly how it's changing. We might even know what A0 and A1 are. So we might, even if we don't know the full distribution, P of y given x, we know the nature of the change. And second, when we talk about model adaptation, the tools that I'm going to be describing, the idea is that, like with domain adaptation, we initially train with lots of samples from the initial distribution or the initial forward model, but then we adapt our learned reconstruction network just using a few samples, but those few samples that we have to adapt don't contain the X's, the true ground truth images, but rather only use data that we can collect, say with our new acquisition protocol. Okay, so before we get into methods, I think some of you might also be wondering, couldn't I just use generative models here? Isn't this sort of what they're ideally suited for? If I had a generative model for all of my images X, then every time I've got a new forward model, A1, I could just generate training samples, XY pairs, using my generative model and knowledge of A1. And then I could train some network in order to do reconstruction using those training samples and my generative model. But when we try this out in practice using what was the best method in this class, we see that it really just does not compete with the quality of the reconstructions that we can get for our method. And this is true both in deblurring and in super resolution. And the core challenge here basically is that these generative models still at this point aren't able to learn the whole distribution over the space of images with a limited number of samples. Okay, so for our approach, we've got two that I want to propose. The first is parameterize and perturb, or P and P. So the idea is that our learned reconstruction network, remember it had some parameters phi that would correspond to weights of a neural network, for instance. What we're going to do is we're going to perturb each of those weights by some delta. And what our goal is to use our calibration data in order to find a good set of deltas. So if I were to have a particular value of this parameter delta, then I can compute an estimate of an image from my data y, and I can see how my calibration observation yi, and I can see how well my reconstruction using this perturbation fits my calibration sample yi. And so what I'm going to do is I'm going to search over all possible perturbations, and I'm going to choose the one that gives me good reconstruction errors, and which is small. And we want it to be small because we want to somehow exploit whatever's been learned using my original forward model A0 as much as possible. So pictorially, we can think about what's going on this way. We've got our space of ground truth images here in orange, and A0 is mapping those images to this purple space of measurements under the original model. But now at deployment time, we've got a different forward model, A1, which is going to map those images to a new space of measurements under the new model. And so when we do our initial training, what we're doing is we're coming up with a network that maps us back from purple to the orange space. And our goal is to find a new network that's F1 that's going to map us from our new measurements to our ground truth images. And the idea of this parameterize and perturb method is to find an F1 that is effective using our calibration data and which is somehow close to F0. Now the other approach that I'm going to describe takes a slightly different track. It says all that we do with this P and P method is we require that F0 and F1 somehow be close to one another in the sense that this perturbation is small. But it doesn't explicitly account for anything about the relationship between A0 and A1. So in order to do that, what we could do is we could imagine that we could find some mapping, let's just call it G, that could take us from our new measurement space to our old measurement space. And if we could do that, then we could use this network that we've already trained in order to do the reconstruction. So we could take this sort of more circuitous route from our new measurements to an estimate of the image. And this is the idea between our second approach, condition and correct. So what we're going to do is we're going to take our measurement from our new system, and we are going to basically try to condition it, or to map Y1 to what kind of measurement we might have had if we had been in our original measurement space. And then we'll feed that through our original reconstruction network. Now that's not going to be perfect, because obviously there are some things that are lost in this mapping between measurement spaces. And so we're also going to train a correction network that's going to correct for whatever errors are resulting from this top branch here. So this function g that maps from one measurement space to the other is simply going to be computed using the pseudo-inverse of A1 and our original forward model A0. And then we're going to search for parameters of this correction network, theta, using basically the same idea as before. We want to find a theta that gives us good quality reconstructions on our calibration data. And we also want to ensure that the correction is small, that we're somehow leveraging everything represented by our original trained reconstruction network as much as possible. So let's just see these two ideas in action. So in blue, well, first of all, let me just talk about the bottom axis here. So here we're considering motion blur, superresolution, and MRI reconstruction. And for each of those three examples, we consider two different networks, either a UNet approach or a modal approach. Second, what we do is we consider sort of the best case scenario where we train and deploy on the same forward model. So there's no model drift whatsoever. So this isn't really what we're studying, but we can think about this as sort of a gold standard. What would have happened if we could have trained for the right forward model from the get-go? And our goal is to be able to achieve that level of performance using model adaptation. So in green, what we're seeing is what happens if we do no model adaptation whatsoever. We just sort of plug in the new A1 like I showed, but don't adapt the weights or anything else. And we see that this leads to, of course, a big drop in performance. And this is exactly the kind of problem that Anders Hansen's group was worried about. But in orange, we've got our PNP method, and in red, we have our CNC method. And we see that in each of these different settings, they give us a big boost in performance that brings us back to being on par with the performance that we would have gotten if we trained for the right forward model from the very beginning. I also have a more anecdotal example in the MRI setting. So here's my ground truth image. And then just to kind of convey sort of the difficulty of our acquisition setup, I'm showing the inverse Fourier transform, reconstruction, and a total variation regularized estimate, along with their residuals or error images. So now let's see for this problem setup how well we can do with these learned methods, especially when we use model adaptation. So in the top row here, I've got UNet reconstructions, and on the bottom row, or on the third row, I've got modal reconstructions, and then the second and fourth rows are just residuals. The first column corresponds to the setting where we train and test on the same forward model. So again, sort of the gold standard that we hope to be able to achieve. The second column corresponds to this situation where there is model drift, but we do nothing to correct for it. And you can see it can lead to some pretty terrible reconstructions and bad accuracy. But in contrast, when we use these model adaptation approaches, we can significantly reduce the artifacts and get performance that's on par with what we could have achieved if we had been using the right forward model from the beginning. I want to highlight that everything I've discussed so far involves sort of knowing the new forward model and using that to, say, figure out what our right perturbation is. If you don't know what that forward model is, though, we can actually optimize over that as well. And this is true not only with our PNP method, but also with our CNC method. And here are some results highlighting that, where I have, again, what the gold standard of training and deploying on exactly the same forward model. What happens when there's model drift and we don't correct for it, And then the results of our P&P and CNC methods, where we're not only learning how to perturb things or do model adaptation, but also learning what that new model is from the calibration data. And we can see that even when we don't have that new calibration, or even when we don't know that new forward model, these model adaptation approaches can lead to significant PSNR improvements. Now at this point, some of you might be wondering whether we really need to do this adaptation approach as opposed to what I would call an augmentation approach. So let's think about this in the context of deblurring. Imagine that we want to use a network for image deblurring, but we don't know what our blur kernel is going to be when we deploy our system. So what you might imagine doing is somehow training your system to work for many different blur kernels. Build up a blur kernel library and train using that entire library. You might say, well, wouldn't that work just as well? If I just kind of cover my bases in terms of different blur kernels, isn't that good enough? And so we did some experiments with that in mind, and it turns out that no, in general, that's not good enough. So in this plot, the horizontal axis is the size of this blur kernel library, and the red curves correspond to what happens when we use this data augmentation approach. And the solid lines correspond to when this library knows what the final blur kernel is going to be. And the red is when we don't train for that final blur kernel, or when we've got an out of sample blur kernel. And so we can see that when that library of blur kernels is very, very small, then this method can work okay. But whenever that blur, if we've got the right blur kernel in this super small library, but as we increase the size of that blur kernel, things get worse and worse relative to what we can achieve with model adaptation, both when we do and do not know the forward model A1 in advance. So with that, I'd like to conclude and thank you so much for your attention and for the great honor of being able to speak with you all today. Just as a quick recap, we covered a lot of different methods and approaches for trying to understand reconstruction problems using learned models and some of the trade-offs involved regarding sample complexity, leveraging knowledge of the forward model, and different forms of robustness. And also talked about ways to mitigate robustness challenges using things like model adaptation so that our methods work even when the forward model has a small change. I'd like to thank my sponsors, the NSF and the Air Force Office of Scientific Research, and thank you again for your invitation and attention. Goodbye.